Hi, thanks for joining this presentation. I'm Theo. Today I'm going to talk about covert channels for CNC and data exfiltration techniques to evade GuardDuty detection. Before I start, I would like to mention that the contents expressed in this presentation are solely my own and do not express the views or opinions of my employer. So who am I? I have presented at Hack in the Box 16 years ago and I'm glad to be back again this year. I spent most of my working years as a software developer, then moved into sysadmin DevOps kind of role, and eventually transitioned into an InfoSec guy. If you want to reach out to me, this is my LinkedIn ID. Here's the list of items I'm going to talk about today. We will start with an overview of DNS tunneling, network ideas, host-based ideas, and SIM. Then we will explore and improve covert channel technique that makes use of popular cloud services. After that, we'll take a look at how Amazon GuardDuty works compared to IDS and SIM, and also the techniques that we can use to evade detection by it. This is followed by a proof of concept and live demo. Finally, I'll talk about some of the common mistakes that people make when using AWS along with the mitigation tips. First, let's take a look at the timeline of different command and control channels used by threat actors in the last 3 decades. During the 1990s, there were many Unix hacking tools distributed in the form of Perl scripts and C source code. As far as I can remember, they are usually distributed on those Frag magazine websites. If some of you here are old enough, you probably might have heard of red tools like NetBars, Backorifice, and Sub7. Most of the Linux and Windows hacking tools that time were using direct TCP for CNC communications. Back then, networks were simpler because every computer that is connected to the internet gets an individual public IP address. I remember during the late 90s, Sub7 released an updated version that started to use IRC channel for CNC communication. DNS tunneling was introduced around the same time when Oskar Pearson shared his proof of concept on Bugtraq mailing list. For many years, HTTP protocol is used by most malware as the CNC channel to communicate with the attacker's server even today. Until 2014, we started to see reports that Reddit, GitHub, Twitter, and Instagram were being used as the CNC channel. However, these are mostly CNC channels used by malware that run on the end user's personal computers. Most of these CNC channels will fail to work when it comes to corporate servers with strict firewall outbound rules. Among all the mentioned channels, the only technique that is tricky to block is DNS tunneling. When a compromised host wants to communicate with the attacker, it doesn't need to send a direct DNS query to the CNC server. Instead, it sends the DNS query to any trusted recursive DNS server used by the host, just like any normal program would do. What happens is the attacker has already set up a domain name and hosts it using their own authoritative DNS server. So all uncached queries for the attacker's domain name that is received by any recursive DNS will eventually reach the attacker's authoritative DNS. This makes it difficult to block DNS tunneling, because there is no way a firewall can tell if a DNS query is legitimate or malicious. From the firewall perspective, it can only see that all DNS requests are being sent to the same recursive DNS server. The reason that DNS service cannot be blocked because applications needed to resolve external hostnames for various reasons, such as to pull OS updates or access external APIs and so on. Nevertheless, the standard DNS protocol is not encrypted, so DNS exfiltration and CNC activities can be seen by network IDS. What about DNS over HTTPS and TLS then? Well, it depends on what kind of environment we are looking at. Covert channels using an encrypted protocol in corporate office network can be difficult to detect when they use port 443. Because any users can be loading a website via HTTPS protocol. For server environment, encrypted DNS can be detected in the same way as any other suspicious HTTPS traffic with SIEM. This is because data exfil activity can cause a sudden influx of outbound HTTPS requests to an external IP, making it stand out from the other traffic. In this talk, we will mainly focus on evasion techniques in the server environment. Some organizations deploy network-based ideas like Snort, Zeek, or Suricata. These solutions work like Wireshark by picking into all the network packets that flow through them. The detection is not foolproof because they use signature databases and rules to check the packet headers and content. Besides, it has limited insights on encrypted traffic like HTTPS, so it can't tell whether a request is GET, POST, or PUT, and to which URL accept for the IP address. Also, deep packet inspection doesn't scale very well when it comes to networks with high throughput. Another type of IDS deployed by some organizations is the host-based IDS. This type of IDS works by installing an agent inside a server to monitor and analyze various areas like file system integrity, process creation, network connections, and application logs. It is usually difficult to evade detection from it unless you can gain access to the host through some sort of code execution within the same process memory of the compromised service. However, host-based IDS is not widely deployed for a few reasons. For example, there are concerns on performance impact and stability on the host as some of them uses kernel mode hooks. This type of hook can sometimes cause problems to certain applications or crash the whole system if it is buggy. Host-based IDS is usually not very platform agnostic due to the use of kernel modules. And some organizations have servers running very old Red Hat that is no longer supported. In Windows, kernel mode hook is no longer allowed since 64-bit due to patchgut, and Microsoft requires kernel drivers to be signed before it can be loaded by Windows. Another problem with host-based IDS is that it can get quite noisy due to rapid application changes in modern software delivery process. Nowadays, many organizations prefer to use SIEM over IDS, but of course, they both can work together as well. SIEM, in my opinion, it is more powerful as it works at a higher level on top of various data sources. For example, we can feed it with the logs from VPN, AD, DNS, web applications, and endpoint security like antivirus. Then it can aggregate those data to provide insights like traffic patterns for anomaly detection. Alerting rules and actions can also be configured on top of these insights to block an attack automatically. It is essential to have SIEM because it can simplify investigation during a security incident and identify the scope of a data breach, especially when you need to comply with legal requirements like GDPR. We have briefly gone through how DNS tunneling, IDS, and SIEM works. Now we'll take a look at an improved technique for the Covert channel using popular cloud services to evade detection. Most organizations today use some sort of cloud services like GitHub, New Relic, Cloudflare, and so on. For example, if an organization uses GitHub, their CI/CD servers would need to connect to GitHub to fetch the application source code during the build process. The same thing applies when an application needs to send or receive data from any other cloud services. Due to this reason, the IP range of these cloud services are normally whitelisted in their SIEM and allowed by their firewall. To see how these trusted IP addresses can be used by malware, we will need to work backward. Assume that we're the attacker, and our target for data exfiltration is a server running in a secure network. That server sits behind a firewall and does not have any public IP address, the only way it can reach the internet is through a NAT gateway. And that server uses the internet to fetch repositories from GitHub and get OS patches. Let's say we're going to use to compromise that server through a supply chain attack. Before the attack, we'll need to prepare a few things. First is to gather the IP range of the popular cloud services. We don't have to gather the IP range of every cloud service, but we need to pick them based on a few criteria, like look for those that are widely used by many organizations, then check and see if they have their API and IP range documented publicly in their website. And most importantly, the service must have the ability to store and retrieve data. Second, we also need to select a few popular CDN services and gather their IP range. Third, we have to create accounts for these selected cloud services to obtain the API keys for using them, and also set up our CNC server behind the selected CDNs. The last step is to embed the API keys and collect the IP range data into the supply chain malware for later use. In the supply chain malware, the way how it establishes the CNC channel is the crucial part to evade IDS detection. It needs to monitor all the operating system connections for at least 24 hours and continuously look for any remote IP address that matches any of the embedded IP range data. This should be done as often as every 1 to 2 seconds, but it is a very lightweight operation, so it's not going to cause any CPU spike. On Linux, this can be achieved by reading /proc TCP as a file, /proc TCP procnet TCP as a file, sorry. While on Windows, the same information can be retrieved through get TCP table API call. If there is no matching IP address found after 24 hours, the next step is to look into the operating system's package repository config. We want to look for a hostname with IP address that matches any of the embedded IP range data. So now we have 3 possible outcomes. First, if a matching cloud service IP address is found, then the malware can use that cloud service storage as CNC channel to exchange data. Second, if a matching CDN IP address is found, then the malware can use that CDN endpoint to talk to the CNC server that was set up previously. And third, if there is no matching IP address found, just default to any of the selected CDN. And the malware will have to use the endpoint of that CDN to talk to the CNC server. The first 2 outcomes will blend in the CNC traffic as legitimate SaaS usage. This can help to stay invisible from the IDS and SIEM detection. The third outcome might potentially trigger IDS or SIEM alert, but there's a high chance it may be treated as a false alarm. Why? Because when the SOC engineers see an IP address that belongs to a reputable CDN, they might think it is some applications downloading updates that is being hosted behind CDN. I'll now talk about the main topic of this presentation, GuardDuty evasion. Amazon GuardDuty is a managed threat detection service from AWS. According to the AWS website, GuardDuty works by analyzing data source from CloudTrail, VPC flow logs, and DNS. It also uses threat intelligence feed and machine learning to detect anomaly in the AWS account. And one important thing to keep in mind is IAM is used everywhere to call AWS API. Now let's assume that our target for data exfiltration is a server running in AWS and all dependent services are AWS products. To avoid GuardDuty detection, the malware must not call any API service using the compromised host IAM credential. So we don't leave any trace in CloudTrail, and we don't want it to communicate with any IP address that is not trusted by AWS. Also, we can't use DNS to perform data exfiltration since GuardDuty can detect that. So what do we need to establish a CNC channel while making sure GuardDuty is happy? we need a medium for data exchange between the malware and CNC server that doesn't require AWS API. That medium for data exchange must be trusted by AWS to pass GuardDuty's check. The implementation should be simple enough that we don't need any extra crypto libraries for authentication. And it should use HTTPS protocol to blend in, like performing a usual REST API call. Actually, there are many options to evade GuardDuty, but due to time constraint, I'll show 3 of the ways to do it. First option, embed the IAM user access key of the attackers in the malware. This method allows the use of any AWS resources like S3, SQS, DynamoDB, and so on. It is similar to many malware CNC channel, except that the malware interacts with AWS endpoint instead of some unknown IP address. The disadvantage of this option is when someone found the access key in the backdoor code, they can use it to get the AWS account ID and IAM username. Then they will straight away know it is a backdoor the moment they discover that account ID does not belong to them. And this method requires HMAC and SHA-256 algorithm to sign the API request, but it is not ideal to add more code or additional dependency in the backdoor. On a side note, this method will not generate CloudTrail log in the compromised host account because it is using the attacker's access key. The second option is to set up the CNC server hiding behind the Amazon CloudFront CDN. This method does not require signing the request, but the chances of getting detected by GuardDuty is unknown. I've only done limited tests and GuardDuty did not detect it. However, we don't know if GuardDuty might start flagging outgoing connections from EC2 to CloudFront in the future. Amazon Linux 2's YUM repository is hosted on S3 directly, so S3 will be a more trusted service than CloudFront. The next option is to use the attacker's S3 bucket with pre-signed URL. This method does not require signing the request as well, and S3 bucket is preferred since Amazon Linux 2's package repo is using it. Although S3 pre-signed URL has limited validity, but we can work around it. This is the most preferred option among the 3. And let's take a look at how our proof concept uses this approach. Before I proceed to the demo, let's take a look briefly how it works. In this POC, we use a S3 bucket as the medium for data exchange between the compromised host and the attacker. First, the attacker starts a CNC service by generating pre-signed URL as channel files that can be accessed publicly by the malware. The service will keep refreshing the pre-signed URL in these files every 24 hours to maintain its validity. At the same time, the service will also poll the bucket periodically for any session creation request files. This is shown in step 3. Basically, the CNC service is now running and waiting for any compromised host that tries to communicate with it. In step 2, when the malware starts running in a compromised host, it will randomly pick one of the channels and use the pre-signed URL to create a session request file in the bucket. Now step 3 at the attacker's side sees the session request. It will create a private session based on the session ID picked up by the malware. As the new private session ID is created, the malware will now poll for server message using the session ID as shown in step 4. So any messages from the service will be executed by the malware in step 5. And the output is then written back to the bucket with the pre-signed URL. So in the final step, the service will read the output from the bucket to display, and it repeats the whole cycle all over again. Now let's look at the demo. So in my AWS account, I've created this bucket named HITB Security Conference 2021 AMS bucket, as you can see from here. This is the S3 bucket that will be used for data exchange. So here are my proof of concept codes, and now I'll run this CNC server on my local machine. As you can see that, okay, this is my local machine user. So now the service is started on my local machine, and it is making use of the S3 bucket as the data exchange medium. Before I SSH into the EC2 that I'm running in AWS, let me show you the GuardDuty status. So I did a refresh, and we can see that the last seen findings is a day ago, and these are all the sample findings that I generate using the GuardDuty tool. Now I'm going to SSH into my EC2 instance to run the proof of concept malware. Okay, as you can see, this is the IP address that I've created an EC2 earlier, which is here, 3.250.87.30. And this is running in AWS. And earlier I've prepared a file, this CNC client over. I can show you and take a look. So it is kept as simple as possible, only using a HTTP client. And yeah, the proof of concept code can be obtained in the link that I provided in the slide. So the moment I start this CNC client, it will start to establish the session via the S3 bucket that we've created. As you can see that the session has been established now, so it's basically just waiting for a command from the attacker, which is on my local machine. So on my local machine, this CNC service is basically like a reverse shell. Whatever command that I type here will be executed on the malware host. So let's take a look. So you can see that the uname-a, it goes over here on the remote host, and I get an output redirected back. To show again, I'll run who am I. My local user here is Jacko, but on the remote host is EC2 user. And okay, let's check the DSpace. And also list the files in the current folder. This proof of concept can be modified easily to perform file transfer as well. Now let's take a look at GuardDuty again. We can see that there's no new findings here, even though I refresh, and the last seen is the one that is a day ago, because GuardDuty it doesn't detect any actions to or any read or write activity to S3 bucket as malicious. It may take a few moments for GuardDuty to process the logs like VPC flow logs, DNS logs, and also like CloudTrail. So we'll come back again later and take a look again. Let's move on to the final slide. Basically, here are the common fallacy about AWS. First is that many AWS users believe that it is safe to allow all egress traffic to AWS services. The problem is, remember that AWS is a public cloud. Most of the managed resources are shared among different customers. In fact, tightening egress traffic is as important as tightening ingress traffic. So by using AWS private link endpoint, we can restrict the traffic to a specific bucket through the endpoint policy. This will help to protect your host from S3 exfiltration, which makes the earlier shown technique won't work. The second fallacy, using IP tables in EC2 is the same as security groups. This is not true because IP tables of a compromised host can be changed if the attacker got root access on the system. But security groups works at AWS account level outside of the host. Also, when security group is tempered, it can show up in CloudTrail. This allows us to write Lambda function to monitor CloudTrail for any security group changes and trigger alerts whenever necessary. Therefore, it is recommended to use security groups over IP tables. And the third fallacy, having GuardDuty is enough for overall security monitoring. Amazon GuardDuty is good in monitoring a subset of security issues, maybe like 70 to 80% of common threat. Unfortunately, a lot of data breach can happen and stay undetected for years due to the missing visibility of that 20%. So in order to achieve good security visibility, it is essential to continuously tweak and improve the SIEM in your organization. Now let's take a look at the final, do a final check on the GuardDuty to see if it detects my S3 exfiltration demo. So I'm doing a refresh again, and we can see that there's no new findings at all. Well, a final run, we can see that, okay, the uptime, yeah, it's basically still running fine with no detection. So yeah, basically that's all for my presentation. And I'm going to shut this now. See, it got disconnected and shut down the instance. Okay. The proof of concept code can be obtained through this link, github.com/ssto HITB Security Conference 2021 AMS-POC repository. And that's all for my presentation. Thank you.